Welcome to the fourth Agda problem-solving session for the HoTTEST summer school. I will now open Agda, hopefully with this blow high not getting too much in the way. And we will look at the problems. But first, I want to ask whether there are any questions of any kind. Okay, well then let's just get started. So let's see if this is going to work with holding a short. So we are now using new files. We are no longer importing Prelude, we are importing uPrelude. And where this is located is in the Agda/HITS directory. So you need to pull up some new code. And the names of a lot of the things that we were using before got completely changed when we changed instructors. So let's just look at this example, and we have loops. So what is a loop? Metadots, and I navigate to the definition. So in new Prelude, this is lecture 4. Let's see what new Prelude has, just out of curiosity. So there's the definition of the equality type. Concatenation is the hot notation. Inversion is not the hot notation, it's an exclamation point. Then we have app and transport, pointwise equality. And crucially, we have equational reasoning. And equational reasoning will come in very handy, and I'll demo it very soon afterwards. Sigma types, which are universe polymorphic, which is a difference from what we were seeing before. Then equalities on pairs, proposition on pair equality in sigma types. And we also have everything that we saw in lecture, in particular, the definition of S1 as a higher inductive type using postulates and rewriting. So S1 has a constructor loop. I say a constructor, but we've postulated that loop is an equality base to base, where base is some term of S1. And what's going to be relevant is probably within within lecture 4 notes. We can see that we have some properties about paths. For example, and to use topological terminology, multiply, well, I guess more algebraic terminology, concatenate with the reflexivity path or multiply by reflexivity, then you don't do anything to the path up to a higher path. So p.refl is p, refl.p is p, associativity of path concatenation, and left and right inverse laws. And that's going to be relevant in what we're about to do. So here we have loop inverse dot loop is equal to loop. And there are two ways which we're requested to prove this. So this is going to be a multi-step proof. And so I'm going to begin equational reasoning. Now, the first line right here, if I just type that in and I normalize it, I see that it actually normalizes to something without parentheses. And this is just to remind ourselves that when you have a concatenation of paths, within the code, it is declared to have, so in new Prelude, I suppose, infix L, which means that it's left associative. So those parentheses are actually superfluous. Now, how you do equational reasoning proofs, and the way that I like to style them, is that I indent my line, I type in equiv, and then these are typed by \angle bracket. Now, we have loop inverse, so we can cancel those. And the way that we cancel those is with this, sorry, that was in the lecture notes. With this inversion cancellation law, and there are both left and right versions of it. We have the inverse on the right, so we'll be using this version with loop. But the problem is that if I just do this, that's not going to work. Why is it not going to work? So let's see what's missing the other loop, right? So let's see what this thing in the middle actually proves. If I look at this, I've commented out the other stuff. What this proves is that loop.loop inverse is refl. But here I don't have loop inverse. I also have loop. So I need to do something to actually turn it into a path between this starting point and something else. And what I can do is I can take this equality and I can apply a function to both sides of it. And that function will be the function which concatenates loop. Now I've chosen to write it like this. So if you have a operator that is declared as a infix operator, so it has some underscores, you can remove an underscore and then put an argument there and keep an underscore to say, well, this is the function which expects an argument here. And so this will work. There's another way that I can write this though, and that's that I can write app, and then I can just write a function, let's say phi, to phi dot loop. So I guess that's the more traditional way without using this cleverness with underscores. Now, how I do equational reasoning proofs is that I start with a step, I write a justification, and then what's the output of that justification going to be? Well, I don't know. So I put a question mark here, and then an equational reasoning proof always has to end with a QED. So then I can say, well, what's the type of this? And you'll see that the type is the left-hand side equals refl.loop. So that's what I can put in for my question mark. So I never fill these in manually. I just put question marks, then I deduce the type, and then I copy the right-hand side of the equality over from here to here. And so we're not done yet because we want to show that it's loop. But then we have left and right identity laws. And let's see what those left and right identity laws are. So we have this dot units, and it's a left identity law that we want. Applied to what's my argument? Well, loop. And then let's see if that gives me what I want. It shows that it's equal to loop, so that's good. And that finishes that equational reasoning proof. Now, there's a second way that we can do it. We can try canceling this with this, but what do we have to do before trying to cancel that with that? Someone in chat says switch the order of parentheses, and that's exactly right. And the technical term for that is known as reassociating. And so how do I reassociate? Well, let's look at this. We do have some arguments here. And so there's the dot assoc. And it starts with something that's bracketed to the right and rebrackets it to the left. In our case, we have something that starts bracketed to the left. Well, that's going to be my justification, but I guess I want to copy this first. And then these parentheses, once again, are just superfluous because we've declared it to be left associative. So then I can apply associativity, and I have to supply 3 arguments to this: loop, inverse of loop, and loop. Now, is this going to work? So let's see. It's not, because associativity starts with something bracketed in the other way. So I'm going to take this entire path and I'm going to invert it. And then I make some progress. So I've rebracketed it. And now I can cancel these 2 things. So here I'll use the more fancier underscore notation. So I'll app, and I know that I have to app loop dot onto something. Just writing this doesn't work. You have to put in the second underscore. And the path that I'm going to use is the left inverse cancellation law on loop. And that takes me to loop. So we're done. And that's good. Now, there is an exercise to show that the two paths that we constructed here are actually equal. And it says that it's a trickier exercise. And I won't do it right now, but I'll just look at what the goal is. So the goal is when you do equational reasoning, it concatenates these equalities and it concatenates reflexivity at the end. But concatenation is defined so that it computes if you have reflexivity on the right. So the rightmost reflexivity disappears. And what this says is that this step of reasoning followed by this step of reasoning is equal to, and what is this an equality of? Well, if I type in something like this, and I deduce its type, then it's equality of equalities. And that is an equality between equalities between equalities. So 3 level is nested. And so how would we prove that? Well, let's try and do the next exercise and see if that helps. So the next exercise considers this. What if we take the double function, which is, what is the double function? So the double function is a map from S1 to S1, and it's defined by S1 recursion. And so how does S1 recursion work? Well, I have the circle, and what does the circle have? It has a base point, and it also has a loop. So in order to tell you how to map the circle into any other type, I need to tell you where the base point gets sent, and I need to tell you where the loop gets sent. Now, where can the base point get sent? Well, it can get sent to any other point of any other type, right? Now, where does the loop go? Well, what happens is that the loop has to be taken to some equality of wherever that point, the base point goes to. So this is where the image of the base point. And then the loop has to be an equality of f of base to f of base, essentially. And the rule that we get is that if we sort of ask, well, so this is S1 rec. That's the recursion principle. Given a point in a type X and given an equality of that point with itself, you get a map from S1 to X. We have as a rewrite rule that applying S1 rec XP to base gives you X. So this is sort of the eliminator for the circle. And if we apply a fully formed eliminator onto a point in the circle, namely the base point, well, it gets sent to where we say the base point gets sent to. And this principle says that if we apply this to a loop, but how can we apply it to a loop? We can't just evaluate it at loop. We have to use this app construct, which was defined by path induction. So if we app this onto loop, then we get P propositionally. We're not going to use this as a rewrite rule. And so what double is that it's a function from a circle to the circle, which says that the base point gets sent to the base point and the loop gets sent to loop.loop. So the idea is that as you go around the circle, the function takes you around the circle twice. And if we look at what the goal is, it's app double onto not loop is not loop.not loop. But if we normalize this, then we see it's app S1 rec base loop.loop onto not loop is not loop.not loop. Now we know what app of this onto loop is, because that was sort of the postulate into how it behaves. There's a computation rule for how it acts on loop, but we don't know how it behaves on not loop. So what I'd like to show is a general lemma about application. And what happens if I apply something onto an inverted path? So because it deals with application on inversion, I'll write app dash inversion. And I would like to state this lemma as generally as possible. So app considers some function from X to Y, and X and Y can be types. Can I type in type L1? Or do I have to type in set L1? We'll see. Now, I want to make a universe polymorphic, but the problem is at the moment I'm not declaring the variables L1 and L2. And I don't like to declare variables repeatedly at the start of every single function. If I have an L, it should always be an interval variable. Well, there's one way that you can get around that, and that's by making a variable declaration. And so I'll write that if I ever see L1 or L2 in the file, they necessarily refer to some level. And how it works is that this function will sort of get implicit level arguments in front of it. Now, when you're making variable declarations, it's considered sort of unhygienic to have them in this file. If other files import it, then they'll also import this variable declaration. And so it's usually good to make the variable declaration private, which means that it can only be seen in this file. So that's just the idiom. And now this makes sense. So let's see if it's happy. It is happy. So given two types and given a function from x to y, let me move this a bit. That should work. And then given 2 points in x, and given a path from x to y, what I want to claim is that if I app f onto the inverted path p, that's the same as inverting the path app fp. Now notice what I've done is I specifically care about it for the path loop. But in order to prove the lemma, I can't just reduce loop to reflexivity. I have to change what the motive of the proof is. So I generalize the proof to not just being loops, but being any sort of path with 2 free endpoints. And because the endpoints are free, that lets me argue using what? Path induction, exactly. So the key here was that I generalized the statement, because if I looked at what loop was a path x to x. Well, if I have put x equals x here, let's say I just did that. Let's say I tried to prove the theorem for loops. Then if I try to do path induction, it would say, I'm not sure if there should be a constructor for REFL, because the instructor, this rule does not work. The rule requires 2 free endpoints. So we actually have to have an idea, and that's that we have to generalize the result from proving it just from loops to proving it about paths. And this is going to be very important. Well, when it's about paths, I can use path induction. And then I can reduce it to the path being REFL x. And then let's see what I'm supposed to prove. Well, I'm supposed to prove that REFL f of x is REFL f of x. And that can be proven by saying that both are REFL f of x. So REFL of f of x. Great. So that gives me some progress. So we're going to also do this as an equational reasoning proof. And I'm starting off with this. Zoom is a bit in the way. And what I have now is that I'm applying something onto the negation of a path, or the inverse of a path. And I have just proved a theorem about that. So I can use this theorem on this function. This function is also known as double. So maybe I can write it like that. And then the path that I'm inverting is loop. Now, what have I succeeded in proving? Let's see. So I usually put a question mark here and then I see. And it says app double loop. Now, at this point, I probably want to expand what double is. So I'll append 2 CUs in front of that, and I'll get this. Now here, what's happening is that we're applying an S1 rec onto loop. And there's a propositional computation law for how that works. So if we go to the lecture 4 notes, then we've postulated something. And that postulate is S1 loop rec, that if you app an S1 rec term onto a loop, then you get what the second thing is. This isn't a rewrite rule, so I'll just have to actually make reference to it in the proof. So this is being applied where the motive has base and loop.loop, not the motive, but the arguments to the eliminator. And this always talks about when it's applied to loop. But the thing is that I have sort of an exclamation mark at the front. So I'll just app that onto this. And that works. So if I'm applying something, this eliminator onto loop, then the result is going to be what the second argument of the eliminator is, which is loop.loop. And now I've applied exclamation mark to the entire thing. So I get now bang loop.loop. But I want to show that that's bang loop concatenated of bang loop. And in order to do that, I'm going to need to prove another thing by path induction. And it's about bang applied to concatenation. So that's the natural name for it. There's only one type here, so I'll call it X in type L. And then suppose I have 3 points in X, Y, and Z. And then suppose that I have 2 paths, P from X to Y and Q from Y to Z. Then the claim is that if I invert P dot Q, what should that be equal to? So someone said not P, not Q. So let's look at the first suggestion. Not P. By the way, these things are defined with certain precedents, and the precedence works out so that's it's like that. Let's see if this works. Well, they're going to say there's a problem, and that problem is that certain endpoints don't match up. And if we see, then we can't even concatenate these two paths together. Why? Because you had something going from X to Y, and then you had something going from Y to Z. Well, if you invert it, then you have something going from Y to X, and you're trying to concatenate it with something going from Z to Y. But one ends at X and the other ends at Z. So that's a problem. So you actually have to concatenate them in the opposite direction to make it work. Because if you have this followed, sorry, I have to do this followed by this, and then you invert this and you invert this, then it has to be the other way around. So it's actually not P concatenated with, no, it's Q. Sorry, not Q concatenated with no, P. And that checks out. Now, how are we going to prove this? Well, we've generalized this from being a state to being a statement about loops to being a statement about paths with free endpoints. So we can use path induction twice. So right now that's doesn't reduce it fully. It reduces one side because we have .refl there, but the other side still isn't fully reduced. So I guess we could try and prove it using sort of the left unit law. But a quicker way of doing that would just be to reduce both components. And then the goal just becomes reflexivity. Well, then here I can do one more step. And that step is this bang dot lemma applied to the paths loop and loop. And I get what I want. Yes, of course. So the question is, does it matter on which arguments you do path induction? And for example, when we defined path concatenation, we defined path concatenation to be inductive on the second argument. That means if you ever have anything concatenated with refl, it computes. Now imagine that we defined it to be path induction on both arguments. then what would happen is actually, it's a bit unfortunate. If you have anything dot refl, it would not compute unless the first anything was refl. Which would mean that, for example, when we have equational reasoning proofs, we had an extra dot refl at the end, which otherwise computes away. So the proofs that you actually do when defining something like path concatenation matter a lot for computational properties. Okay, now, by the way, now that we've seen this, and we've seen these two lemmas, and we've seen this idea of path induction, we can go back to this trying to prove an equality between this path and this path. And does anyone have an idea as to how we might approach this? So we have loop here, right? And that's a loop. What do you think we can do to sort of make this a more general statement? Replace at least some instances of loop with a generic path is the suggestion. Well, let's replace all of them with a generic path. Let's see if that actually leads to a well-defined type. The name is only going to be in scope here, so I don't have to be very clever about what I name it. And let's make this sort of like fully general. Let's say for any type X in type L, and let's say for any 2 points, x, y in X, and for any path P from X to Y. And then what are we going to claim? Well, let's see what we're trying to prove here. We're trying to prove this equals this. Let's just copy that over. And let's see if we can replace all of the loops with just P's. Is that a well-defined path? So as it will turn out fortuitously in this example, it will be a well-defined path. And this trick would not work unless this were well-typed. Are things defined only? Missing a closing bracket. Oh, I see. Whoops, what's going on? It's giving me a level error, so I think it might be a bit different. I think the problem might be that when we look at lecture 4 notes, and we look at what the proof of this is, then it only applies to types. It doesn't apply to our types at arbitrary level. So I'm going to go back and I'm going to remove this level argument. And then I think that I'm not missing a closing parenthesis. So that wasn't the issue. But okay, because we can generalize this, what we're trying to prove, to being about arbitrary paths instead of arbitrary loops, we can do path induction, and then everything computes. So if I reduce it to refl x, what's the goal? The goal is to prove that refl x is refl x, and y are both things refl x because they're both refl x, or y are they equal because they're both refl x. So refl of refl x with an extra parenthesis. But that means that by path induction, because we were able to generalize it, and only because we were able to generalize it, we can just apply this to loop. And then we get exactly what we're trying to prove. So that's pretty neat. Having solved this exercise and seeing how important it was to generalize things to being about paths with free endpoints, we see that it lets us sort of just automatically prove this higher coherence between these two paths just by path induction, because we were able to make both endpoints free in the statements. So the key was generalizing the statements, and that's something that happens a lot. Okay, let's do, this is a pretty simple exercise. what happens if we just want to define a path that takes loop to loop inverse? Well, let's see how we define any sort of map from the circle to the circle. We are going to be using S1 rec. And so we need to say where base gets sent and where loop gets sent. So we want to send base to base, and we want to send loop to loop inverse. And that should define a map S1 to S1. So that defines a map that sends loop to loop inverse. So this is just a bit of practice in actually defining functions from the circle, in this case to the circle, using the recursion principle. Okay, and now there are some exercises. So let's see how we are for time. We're good for time. Right. So now let's look at the lecture notes. So here we defined a second presentation of the circle, where this circle has north and south. And then it has east and west, which are paths from north to south. And the recursion principle for it is that you have to say where north gets sent, you have to say where south gets sent, and you have to say where west and east gets sent. And they're paths from the image of north to the image of south, respectively. And then there are associated computation rules, some of which are propositional. Then we define to and from. To is a map from the circle to S1 to circle 2. And where loop is going to go is, well, it's going to first trace, so the east path, and then it's going to trace the west path backwards, because east is a path that goes from north to south, and west is a path that goes from north to south. Well, if we want to send the loop around, we do east and then we do west inverse. And let's see the path in the other direction. In the other direction, we have to say from, well, where are east and, so now we have two paths here. If we send both east and west, well, so first off, where do north and south get sent? Well, there's only one point that we can name in the circle, and that's base. So north and south are both going to get sent to base. Now, where is east going to be sent to? East is going to be sent to, well, here it's REFL base. Well, where is west going to be sent to? West is going to be sent to loop. Now, we can't send both to loop because otherwise we'd, I guess, do the loop and then do the loop backwards. And so it would actually be a trivial map if you did that. I'm surprised that we're not sending this one to loop instead of that. So we stand still on half of the path is the key. And so that defines the maps to and from. And the exercise is to prove that both of these are homotopic to the identity. Well, rather, it's to prove, not that both composites are homotopic to the identity, but rather that one of the composites sends loop and base to the correct points. And then we're going to be able to prove that they're equal, which isn't an exercise here, but which we'll do. So let's just look at to, from, base, and base. Well, how is to? To sends base to base and from, to sends base to north. And from sends north to base. And both of those rules were probably rewrite rules. So I bet that this is just reflexivity. And yeah, if I fully normalize it, it's just reflexivity, because both of the computation rules for those recursion principles were used in rewrites. So they're definitional. Now, the much more tricky thing is to prove that this is true for the loop as well. And so usually before you think about like, well, what this proof is, we can just ask Agda to unfold everything. And so what happens is that when we app to loop, where that's going to get sent is, well, propositionally, it's not going to be sent definitionally anywhere. But there's it gets sent somewhere propositionally. So if we expand everything, this is what it looks like. At the moment, let's just keep this as from and deal with to first. Any questions? So what we have is that we're apping S1 rec. And so we have the computation rule associated with that. And we used that before. That was S1 rec loop. So the base point is getting sent to north and the path is getting sent to east dot west inverse. And that already forms a well-formed proposition, except we're apping from onto this. So what's going to happen is that we're going to have to app what? We're going to have to app from onto that. And that gives me something. That's app from to, well, now we propositionally computed this as the loop gets sent to east dot west inverse because that's where it was defined to be sent by this recursion principle. Now, at this point, we want to expand what from is. And we see that that's circle rec 2. However, before we expand it to be circle rec 2, this is a concatenation of two paths. And if we want that to compute, I'm going to do something fancy and I'm going to use the app to function, which is going to let me rather no. Okay. App concatenation is defined in lecture notes. In the lecture notes, we have a proof of app concatenation that if you app f onto a concatenated path, it's the same as concatenating f of p and f of q. So the function is from, and the first path is east. I don't need parentheses. And the second path is the inverse of west. Sorry, let me just look at what the definition of that is. The function is implicit. Would you imagine that? That's a pretty bold choice. Good. So that distributes the app across. And we have this. Now let me just reduce the second thing to being not of something. And the way that I'm going to do that is I'm going to app this thing. You know what? I'll just do it. Yeah, no, it's this thing. Underscore. And then I'm going to use the app not computation rule, where I made the function explicit. And that brings the path inversion out front. And now I'm going to do something fancy, and I'm going to apply something twice. So I'm going to do app underscore 2, and I'm going to apply a function that takes two arguments. And that function will be lambda, let's say, phi and psi to phi dots exclamation point psi. And then it'll let me do a path in both of these things. So if I look at app from east, well, at this point, it might actually be useful to expand what this is fully. This is circle to rec, and it's applied to east here, and it's applied to west. And there are propositional computation rules for both of these. So I have to go to the lecture to see what those propositional computation rules are. And then it's circle rec west and circle rec east, respectively. So I see here that I have east. So first I'm going to do circle rec east. And I need to specify for this where all 4 arguments are. And it's sort of long. That's what the 4 arguments are. And then similarly, here I have west. So it's going to be west with the same motive. But just to see that's a sanity check as to what we're doing is correct, and this is something that I do often in proofs, I just comment out the entire equational and reasoning proof that I have, and I want to see, does this step make sense, or does part of the step make sense? And so I copy this over here, and I see what its type is. And its type is that if you're apping the circle to recursion with a certain arguments, where those arguments are the arguments that I have here, onto east, then I get loop. And that is what I want. So I think there shouldn't be mistakes, and that this should actually give me something. And it does give me something. So if I actually do not normalize this at all, it gives me loop dot inverse refl. But inverse computes on refl, and this computes. So it actually just becomes loop, and that finishes off the proof. It's really loop dot inverse refl. Any questions about that? Sure. So the question is just about how I've been using the words rewrite and propositionally. So what happens is that in lecture, we have these higher inductive types, but how are these higher inductive types? Does the system support higher inductive types? Well, it doesn't, so we're just going to postulate them into existence. So we're just going to suppose that S1 is a type that has loop and that has base and loop. And then what happens is that there is going to be, well, how do we use this type? Well, there's a recursion principle. And then there's a thing that says, well, for example, if you use the eliminator on X and P, and you get a function from S1 to X. So what happens if you evaluate this function on base? Where does that get sent? Well, that should get sent to X, right? So this is known as a computation rule because it expresses how an eliminator should reduce. What is a computation rule in general? Well, there are eliminators and there are introduction forms. And so what happens when you apply an eliminator to an introduction form is that there's a computation rule. So for example, what happens if you apply a projection onto a pair? What happens if you apply an argument onto a lambda? A lambda is an introduction form, an application is an elimination form. A pair is an introduction form, a projection is an elimination form, etc. Right? It exists because I say so. That's exactly what we're doing. However, that's not what's going to happen in Cubicle. And I can show you Cubicle at the end of this lecture, just as a preview of what's going to come later, because then you don't have to postulate it into existence, and that's the right way to do it. But it's a bit hard to understand. Right. Why are there both a primed version and a non-primed version? Well, the primed version basically shows what happens if you don't have rewrite rules. So if this is something that's just propositional, then saying that this is equal to P, it's actually not well typed to say that that's equal to P. So if I sort of comment this out and I make this into a whole, and I comment this out. And I look at that hole, then the type that this has is, well, actually, this is sort of bad. Because the Agda is applying the rewrite rule, although it's only rewriting it later. This does not actually have type x equals to x. The actual type that we're trying to prove, well, P has type x equals x, but what we're trying to show is this type. And without the rewrite rule, this isn't equal to x because we've only propositionally assumed it. So if I try and fill this, this rewrite rule should actually not go through and it's going to give me a type checking error. Okay, this is Agda being bad. And see, it lets me fill the hole. Agda does this very frequently. It lets me fill the hole, but then when I reload the file, it gives me a type checking error. And that's an Agda bug. But the reason that it's giving me a type checking error, which is correct, is because the rewrite only happens here. Although Agda's letting me fill the hole, assuming the rewrite rule, which is bad. Agda shouldn't be letting me do that. But retype checking the file, that always keeps you honest. And there are no obvious bugs with that. So here you actually have to concatenate with showing that both endpoints match up. And that's using this propositional computation rule twice. Well, you're by using rewrites, you turn a propositional computation rule into a definitional computation rule. And then you get this unprimed version, which is much simpler, where you don't have to conjugate by the propositional computation rule for base points. So that explains rewriting and propositional and definitional computation rules, I think. Any more questions? Yeah, so abstract over loop trick. Well, I mean, in Cubicle, you literally have path over, and that's great. But that's going to be path over in regular Agda means transport. What is the abstract over loop trick? What does that refer to? Oh, I see. Okay, let's try that. Well, the problem here is that oh, so you're going to claim that applying this to any path is equal to any path. So let's say X and Y are points in S1, because otherwise this doesn't make sense. And P is a path from X to Y. And let's call this lead hex. And so we're going to apply this to P, and we're just going to see what type that gives us. So that gives us from 2x is from 2y. And I guess we can, you know what, let's just try and prove this results in general. Let's try and prove this results for all x. Well, okay, we'd have to prove it for all x, which would actually involve induction. So this right now, we need to generalize the previous result as well. And what generalizing the previous results will actually accomplish is that it will require this proof in generalizing it. So right now, this is not well formed. Right? So you have to generalize this, but when you generalize this and say for all x from 2 base equals base, well, that's just sort of saying that there is a pointwise equality. Anyway, okay, you know what? Let's prove that results. Let's prove the result that we're talking about. That's what I actually said that I do next. And that's the results. Let's say, one of the names of eta or epsilon is correct. Well, actually, that's defined as a constructor. Anyway, lemma. I don't want to come up with names. And the lemma is going to be for all x from 2x equals x. So let's see how we prove that. Because that's what we need to even generalize the previous inductive hypothesis. And basically, x is a point in S1, right? So how do we define a point for, function from S1 to something else? We define it by recursion, right? However, this is a dependent function. And if we look at the lecture 4 notes, we do not have a dependent eliminator at the moment. So we're actually unable to prove this theorem unless there's a dependent eliminator. And this is recursion, not induction. So we can't do it unless we define dependent eliminators. But if you do define a dependent eliminator, then as it'll turn out, what amounts to proving this with the eliminator is that you're exactly going to need these two proofs. That's the catch. So you can't get around actually doing this calculation because there is something to prove. Because if I change the definition by just a bit, it would stop making sense, right? If I, for example, instead of having reflexivity and loop, I made both of them be loop, then it would be sort of doing a path and then doing it backwards. And then that would just be the identity, homotopic to the identity, homotopic to a constant map. And that's bad. So there is actually a proof to be had because we use some property of the definition. So it can't just reduce to path induction. Does that make sense? Good. Excellent. So I said that I'd prove this next, but I can't prove it because this is a dependent function and I don't have the dependent eliminator. I only have the recursion principle, not the induction principle. So it's 54. And I guess at this point, I can just show you a thing, which is some cubicle. And let me just quickly see what my imports are. My imports for cubicle are these. Oh. What? Okay, there is, I have to create this file in a different location. You know what? Yeah, so it changes the namespace. So as to answer Jacob's question, the type that you typed, it's not even, that's not well typed. Okay, this should be better. So let me show you what the circle is. We'd say data S1 is a type where, so it's going to be like a regular inductive declaration. Base is a point of S1. And loop is an equality base to base. Great. Look, so we have higher inductive types. That's great. Let's define a function like double. this is going to be a map from S1 to S1. How is double going to be defined? Well, I'm just going to write an argument in S1, and then I'm going to do case split. Sorry, X. And bam, it case split. So look at that. That's amazing. So I need to say where base gets sent to base. And then I need to say where loop gets sent. Well, I need to say where an arbitrary point on the loop gets sent, where I is an interval variable. Well, I'm going to say that that gets sent to loop at I. And then let's say I have something like example. And let's say I want to compute double on, well, before it asked us to compute double on loop inverse, right? So let's see what that normalizes to. Sorry. Of course it doesn't. App double onto, yes. Well, that's not very friendly. Oh, right. I see. Okay, fine. So this is not a very familiar expression, but let's just write example is a proof that app double of loop inverse is equivalent to loop inverse dot loop inverse. And you can see that those two expressions match up. No, they don't. Because there is nope. Okay, this is not the best demo, but what happens if I do loop dot loop? And I claim that that's equal to something. Well, let's normalize this. That's also not a very enlightening expression. But what happens if I type in loop dot loop dot loop dot loop, and I put equalities around parentheses around these? That works. So yeah, that is definitional. They did, and it's because of Ada expansion and some implicits. However, let me just show you, sort of normalizing paths is bad. Let me show you something better. Let's define a function. Oh no, okay, there's a bit more machinery that's necessary to do that. Anyway, so I hope that you enjoyed today's tutorial. This is just a preview as to what's coming. You're able to define functions like this. But then as you saw, it's not all cherries and roses with cubicle. There are some complexities, and you got a bunch of HComp expressions. So if you're asking why did we start with cubicle right away, then you've just learned why, right? Although cubicle is actually much, much easier to work with overall. Are there any other questions? Okay, I am going to stop the recording.